Welcome, everybody. Welcome to the High Energy Density Science Center Seminar Series. I am pleased to have with us today Dr. Todd Ryder. Dr. Ryder received his bachelor's, 2 master's degrees, and a PhD from MIT with his PhD thesis on deriving fundamental physics limitations on plasma fusion systems. For many years, he was a senior staff scientist at MIT and has also done research on advanced rocket propulsion, biosensors, antiviral therapeutics, science history, and other areas. He has been published in Science, Physics of Plasmas, the Journal of Propulsion and Power, and elsewhere, and featured in the New York Times, BBC, Der Spiegel, and other media. And he now teaches and also has his own consulting company, the Ryder Institute. Please be aware today's talk is being recorded, so if you're uncomfortable with that, please log off. Also, it is an open, unclassified meeting, and be aware of any export control issues. If you have any questions, you can put them in the chat field and I will read them at the end. Or if you prefer, you can just send it out to me and I will call on you at the end. Otherwise, I hope everybody enjoys, and please take it away, Dr. Ryder.
Yes, thank you very much for inviting me. I really appreciate it. So as motivation for this presentation, let me explain why this is important. Current fission power approaches are not ideal. As we know, they produce a politically incorrect amount of radioactivity both during and even for long after their operation. And fission reactors can be quite expensive to build, especially these days. And unfortunately, current fusion power approaches are also not ideal. They're still relatively radioactive. They're much more expensive even than fission reactors, especially in the case of something like ITER. And what many people don't realize is that we've been trying to make fusion work for over 90 years now, going on a century, and yet it still seems to be decades in the future for practical fusion power plants. So with that as motivation, I'd like to try to rederive nuclear power from first principles, and at each step along the way, look for something better than what we've already been trying to do. So here's the wish list of characteristics for the perfect nuclear energy source. If you had your preferences, you'd like something with little or no radiation or radioactive waste, with minimal shielding, something that's scalable to power everything from computer chips to gigawatt reactors, very high efficiency direct conversion to electricity, something that utilizes readily available fuel. You don't have to go to the moon to find it, something that can't explode or melt down or otherwise frighten Jane Fonda, and something that would not be either directly or indirectly useful to terrorists or to unfriendly countries. So the question is, can we come closer to meeting those goals than what we have now? And so it helps to understand exactly why nuclear energy is so much more potent than chemical energy. It all comes down to size. The protons and neutrons nucleus are a factor of 10 to the 5 closer to each other than the electrons orbiting, which give us chemical energy. So you get that from Coulomb's law, or if you do it by the Heisenberg uncertainty principle, you get about a factor of 10 to the 6 from the confinement. So nuclear processes rearrange the protons and neutrons and release 10 to the 5, 10 to the 6 more energy than chemical reactions. You get MEV instead of EV.
So what is it I want to do? I want to
So you get MEV instead of EV energy per reaction. That's great for producing energy. It's bad, though, because it means that a single nuclear particle from reaction has enough energy to break 10 to the 5 to 10 to the 6 chemical bonds, which can activate components in a reactor. And also, some of us are rather attached to our DNA. Then it also helps to understand exactly where that nuclear energy comes from. So if you look at the binding energy, there's a factor for the binding of nucleons to their nearest neighbors by the nuclear strong force. There's a correction factor. Nuclei at the surface, nucleons at the surface have fewer neighbors. And then there's a correction factor for Coulomb repulsion among the protons, which tends to favor an excess number of neutrons. There is another correction. The neutrons behave like fermions, pile up on top of each other. The protons behave like fermions, pile up on top of each other. That tends to favor having about the same number of neutrons as protons. And nuclei are happiest when they have neutrons that are paired with each other, protons that are paired with each other. So there's a pairing energy there. And finally, there's a correction from the shell model. You get bonus points for having magic numbers of neutrons and protons. So you can map all that, look at the binding varies with the proton number Z, the neutron number N, so any place you can move downhill, you can release energy. So there are all these various processes that release nuclear energy. We'll mainly talk about fusion, but I want to come back to the others toward the end of this presentation. Here are all possible fusion reactions. This is assuming that we have relatively stable nuclei, so excluding things with a very short half-life, excluding the possibility of three-body fusion. And of these possible reactions, the ones that work relatively well are the well-known DD, deuterium-tritium, deuterium-helium-3, plus neutron absorption and a few things. Those are in green. There's some things in yellow that are awfully tempting, but they don't seem to work quite well enough. But people still keep reaching for them. And then in red are all the reactions that just don't work well enough. The Coulomb repulsion for the protons is too high, or otherwise they have the wrong number of protons or neutrons. It also helps to understand where the fusion cross-sections come from. And contrary to popular belief, the fusion cross-sections did not come down to us from Mount Sinai engraved in the NRL plasma formulary, but rather we can actually see where they came from. There's a factor in the fusion cross-section for the diffraction-limited cross-sectional area for the wave functions of the colliding nuclei. There's another factor for the spins of the colliding nuclei. There's the probability of tunneling through the Coulomb barrier. And then finally, there's the chance that your compound nucleus that you temporarily form just happens to be at a preferred excited state energy for the compound nucleus. So we can look at all these factors and think about, is there a way to improve this one? Is there a way to improve that one? So for the first factor here, obviously it depends on the masses and the energies of the colliding nuclei. But the question is, are there any other ways you might be able to influence that? I can't think of anything, but maybe you folks can. For the spins, when you average overall possible spins, for most fusion fuels, that gives you about a factor of 2/3 or so. So if you had spin polarized nuclei, you'd improve things essentially by 50%. People can do that, but then the nuclei depolarize too quickly. And this has been examined in the past, but I think it's well worth investigating further in the future. Can we really experimentally nail down exactly the benefits of spin polarized fusion, the best ways of producing spin polarized nuclei, and exactly the depolarization rates from the various mechanisms? Then for tunneling through the Coulomb barrier, you could potentially try to shave off the outer edge of the barrier, make the barrier narrower from the outside. And the best known way to do that is muon catalyzed fusion, using the fact that a muon is like an overweight electron, about 200 times the mass of an electron, so it orbits much more closely to the nucleus, brings things closer together. Unfortunately, the energy required to produce a muon is quite large with known methods. And unfortunately, the energy you can get out from muon catalyzed reactions is significantly smaller than that before your muon goes kaboom. So are there any ways you can improve that? People could potentially investigate that more in the future. You might also consider other things other than muons, but we know that tau particles are even harder to produce and even shorter lived, similar problems with antiprotons. People have considered trying to get the effective mass of electrons in solid state physics to help, but so far it doesn't seem to help. And of course, regular electrons will provide some screening, but unless you have a good way to build a white dwarf, your screening from electrons is usually less than a keV of bonus energy for the ions. Then you could potentially shave the inner edge of the Coulomb barrier. There's a very ingenious proposal from Perkins at Livermore over 2 decades ago for how to do that, and relied on the fact that the boron-11 nucleus is very prolate, So if you approach it from the end, it's much more advantageous than approaching it from the side or angle averaged. But if you assume that your increase in radius is essentially a factor of 1.5 approaching it from the end, you plug that into the handy-dandy formula, you find about a twofold increase in the fusion cross-section, which is good. It's less than predicted by this paper, which relied on an inverted parabolic potential that's only valid at higher energies. Unfortunately, though, scattering bites you, it randomizes the orientation of the nuclei and the directions of the proton velocities much faster than things fuse. But maybe there's some way to use this to improve this. Are there any other ways to beat the Coulomb barrier? I'd love to see people brainstorm for other ways to improve this, because you lose so much performance on this factor. Related to the barrier and the resonance, people have proposed resonant tunneling, like a resonant tunneling diode, that the incoming nucleus has a wave function. You get constructive interference as it rattles around in the target nucleus, and that improves the probability of getting in. It's not clear to me exactly how strong this effect is, or whether this is already baked into well-known cross-sections we have, or whether you could produce this effect if it would really be useful, or maybe the resonance is too narrow or only occurs in an energy range you can't really access. But it's interesting to investigate this further. And then finally, for the resonance within the compound nucleus, are there any ways you could influence that in practical terms? Could you mess with the nuclear angular momentum or the shape of the nucleus, the magic numbers? Could you apply some field or some combination of fields? Could the nucleus capture a particle to make it more likely to do what you want it to do? Could you add extra energy and then extract it again at the end? I think these are worth thinking about, at least. So you're kind of stuck with the cross-sections we have, and then you want to use those to best advantage with the ions. But unfortunately, the ions won't behave. What you would like the ions to do is to be in a highly anisotropic velocity distribution, so they all collide head-on. But as we know, that's not really practical. Collisions tend to mess with the distribution. You also have instabilities if things are highly anisotropic. So that leads to very relatively isotropic distributions, which kind of smear the cross-sections over a range of energies. And then we'd like the ions to be monoenergetic and all of the optimal energy, the peak of the fusion cross-section. But again, collisions smear things around much faster than fusion happens. So you have something that's Maxwellian or very nearly Maxwellian. And then finally, it would be nice to have two ion species at different temperatures or different mean energies. For example, if you're burning dihelium-3, you'd like to keep the deuterium cold and suppress DD side reactions that produce neutrons, only have hot helium. But if you try that, the temperatures of the ion species equilibrate much faster than fusion. All this is in my thesis in one of my physics of plasma papers, if you're curious about this. And so that's how we ended up with the averaged fusion cross-sections that we all have to live with. Next question is the electrons. You can't really live with the electrons, you can't live without them, as the Muppets sang once upon a time. In terms of why you can't live without them, if you try to do without electrons, then the ions with their positive charge are limited to the baryon density, how much you can smush in with a certain magnetic field. And so even for very strong magnetic fields, you'd be limited to fusion power densities on the order of 100 watts per cubic meter or so. So you need electrons, but you can't live with electrons either, because the electrons are constantly stealing energy from your ions. You want the ions to have as much energy as possible. You very nicely give it to them. The ions turn around and donate the energy to the electrons. So you lose a lot of energy that way. It's bad enough if there's one electron for every ion, if you have hydrogen isotopes, but if you go to dihelium-3 or proton-boron 11, suddenly you have lots of electrons running around and they soak up most of the energy. But if I haven't depressed you enough, it's actually worse than that, because the electrons turn around and give their energy to the photons by Bremsstrahlung and by other mechanisms. you can try to keep that photon energy confined, but if you do, then the photons end up with a temperature in thermal equilibrium with the ion temperature, and the photon energy goes up like T to the 4, whereas the ion energy only goes up like T. So above a certain temperature, most of your input energy is just going into making the photons hotter and not making your ions that much hotter. So that limits you to energies of a few tens of keV at best. So you need the photons escape, but if you do that, then that is an obvious energy loss if you're losing Bremsstrahlung and other things from the plasma. So you can find the theoretical minimum Bremsstrahlung loss for a given fuel at a given ion temperature. It does depend on the Coulomb log, which would be about 20 for magnetic fusion, about 5 or so for you guys. But otherwise, it's fairly independent when you compare this to the fusion power. So you find your equilibrium point where the electron temperature settles out, and turns out that you can beat Bremsstrahlung for DT, for dihelium-3, for DD, either with or without product burnup, but you apparently cannot beat it, even in the best cases, for PB11, for helium-3, helium-3, p-lithium-6, and the other advanced fuels. So this really limits the available fuels. What if you try to keep a plasma out of thermodynamic equilibrium? As I said, it'd be nice if you had one ion species that was a lot hotter than the other. You might try to recirculate power back and maintain that. Or it'd be nice to have ions that are a lot hotter than electrons. It'd be nice to recirculate power and cool electrons and maintain that. Or it'd be nice to maintain a monoenergetic, non-Maxwellian distribution. You have to keep herding cats in order to do that. In all these cases, you can think of this as essentially a thermodynamic process, a heat engine that is extracting energy from the plasma, from the parts of phase space you don't want it to be in, putting the energy back in where you do want it to be. You're extracting entropy as well, so there's a certain efficiency to this. And if you work out the power you'd have to recirculate to do this, it ends up being about 1 or 2 orders of magnitude more than the fusion power. So you can only do this and get away with it if you have an extremely efficient system to do it. And so far, nothing people have tried is efficient enough. You lose too much power in the process. But perhaps you could investigate this further in the future. Well, how about stars? I mean, the sun makes it look so easy. Why can't we just do what the sun does every day? The problem is that stars can get away with things that we can't get away with in the lab. So in the sun, the fusion power density is about 83 watts per cubic meter, very low. Core, or averaged over the whole sun, it's less than a watt per cubic meter. The sun takes about 10 billion years to burn up its fuel. Sponsors tend to get a bit impatient if you wait 10 billion years to burn up fuel. For all of its mass and gravity, it only reaches about 1.4 keV in the core. It has great advantages on confinement. The mantle helps to confine the core, and the gravity confines the mantle, works out very well. It is in equilibrium with the photons, which might be a problem, except the photons are so nicely trapped by the optical opacity here, it avoids that problem. How about H-bombs? Well, H-bombs work very nicely. Just so I don't get banned from YouTube, let me point out that everything I'm saying here comes from purely unclassified references. Of course, nowadays you can probably find everything you need to know about H-bomb design from TikTok videos. But if you look at H-bombs, they have the advantage of doing things you can't do in a reactor. An H-bomb can use a fission bomb as a compact, self-powering source of input energy. A reactor can't get away with that. The fusion and the fission reactions work together very nicely. They play well together. That generates a lot of radioactivity, which is good if you're trying to kill people. It's bad if you're trying to build a reactor. The large size of bombs, relatively speaking, aids the energy confinement, but of course also makes the yield far too large for a reactor contain. And likewise, the large size of the bomb slows the expansion of the plasma, but again, it makes the yield much too large for a reactor. So we're down to ICF, laser fusion. And that has a number of potential problems as I see it. You guys have already had quite enough difficulty getting DT to work. Fuels other than DT would be potentially orders of magnitude even more difficult. For DT, my understanding is that NIF, as of over a decade ago, cost over $5 billion. And as I'll show you, it's still many orders of magnitude away from being a full-fledged reactor. Everything in a full-fledged reactor would have to be built to withstand the explosions, which would be equivalent to perhaps a quarter ton of TNT or so. Those would be going off several times per second, round the clock, around the year. And those things that would get shaken and broken by that would have to be replaced, but those are the things that are going to be most radioactive to handle. The first wall in ICF reactor would have to withstand an input or a peak power about 10 to the 10 times higher than in a continuous reactor like a magnetic fusion reactor. Another practical problem is how you open and close the driver beam injection ports, the target injection ports, several times per second, and yet shield them from damage by all these large blasts. And then you have to find a good way to take lithium breeder material from the walls, convert that into very precisely fabricated pellets, get those pellets precisely located in the chamber, and do that with a throughput of several per second, or like hundreds of thousands per day. I can hear the knives out there being sharpened already. So my understanding is that in December, you got a little over 3 megajoules of fusion energy from a shot. And so compared to the UV laser energy of about 2 megajoules, that was a gain of about 1.5. If you compare to the laser IR energy, the gain was less than 1 though. If theoretically you had a driver with 50% electrical conversion efficiency, your gain would be about 0.39. But with the driver you had, the gain was less than 1% by my calculations. Actually, it's worse than that. You could convert.
So Ed Drazen wants me to make these HTPB-coated particles that he found.
Please hold questions for the end. Please hold your torches and pitchforks for the end. So it's actually worse than that because there was 3 megajoules of total fusion energy. If you're converting to electricity using a thermal cycle, you get about a third of that, so about 1 megajoule. So you do the math with the system you have, you are getting a gain to electric of about 0.0025. And of course, a real power plant would have to not only support itself, power itself, but power California as well. And so by my calculations for a power plant, compared to where you are, you would need to increase your gain by about a factor of 1,000 or so. There are other interesting implications here. So your 3 megajoules of fusion energy per shot is equivalent to about 0.75 kilograms of TNT going off. And again, assuming thermal conversion efficiency of about a third, you have a 3 gigawatt thermal or 1 gigawatt electric power plant, you'd have to have about 1,000 shots per second at your 3 megajoules, or 100 shots per second at 30 megajoules, or 10 shots per second at 300 megajoules, or 1 shot per second at 3,000 megajoules per shot. We start working up very large yields per shot, so hundreds of kilograms of TNT equivalent. So it's really a question of exactly how much you can withstand in a reactor, again, especially with several of these things going off per second, every second around the clock. So NIF now is producing, on the order of 3 megajoules per day, if you do one of those shots per day, as I believe you have been doing or could do. But a power plant would need to produce about 3,000 megajoules every second, or about 2.6 times 10 to the 8th megajoules of total fusion energy per day. So where you are, where you need to be, you would need to increase the daily energy output by about 8 orders of magnitude. So it's taken ICF over 60 years to get where you are. As of over a decade ago, NIF had cost over $5 billion. It'd be interesting to know the true cost now. It might be around $10 billion or so. And yet compared to NIF, compared to all that, you still need to increase the gain by about 3 orders of magnitude and the fusion energy per day by about 8 orders of magnitude to get to a power plant. So if you do that, how much would a power plant that actually does all that, how much would that cost? How complex would that power plant be? How many decades in the future would it be before you can actually build that power plant? And why could you convince lots of electric utility companies to buy a power plant like that instead of cheaper or simpler or more readily available power plants that use renewable or fission or fossil fuels? By the way, if any other organizations are out there are interested, yes, I am available as a demotivational speaker. So at least in my opinion, I do think that NIF is useful. So, please don't misunderstand me. I do think that NIF is useful, but in my opinion, I think it's most useful as a wind tunnel for scale modeling of nuclear weapons or astrophysical processes, things like that. I think it's also potentially quite useful as a WPA project in order to attract and retain people with the expertise relevant to produce nuclear weapons. In case we have some emergency in the future, we need to send Bruce Willis to an asteroid or something. But don't worry, the plasma is not that much greener on the other side of the confinement system. If you look at magnetic fusion, it starts off as a nice simple idea. Particles will spiral along the field lines, and they tend not to cross the field lines, so you can keep them trapped. But as the Livermore mirror program found many decades ago, you lose too much from the ends. So you solve that first problem by having no ends, by wrapping it into a toroidal shape. Now there's a second problem. Grad B and E cross B drifts together let the particles escape. So you solve that second problem with a new solution. You add a second magnetic field, a poloidal magnetic field. But now there's a third problem. You still have particles escaping, but now it's by hoop and tire tube forces. So you solve that by adding a third magnetic field, a vertical field. So all the tokamaks and stellarators and field reverse configurations and things really kind of vary on exactly how they generate these, but they all have to generate these multiple magnetic fields and plasma currents and things. It's quite complicated. And then it's further complicated when you consider that in addition to all this, you still have to get your fusion fuel in, you still have to get your energy in, you still have to extract your fusion energy from it, and you still have to find some way to have like a lithium blanket and breed tritium if you have to do that. So it gets quite complicated. This is not necessarily impossible, but it's really, really hard to do. What about other confinement of fusion plasma? Electrostatic confinement does not work. I looked at that in quite detail a long time ago. Electromagnetic confinement could work, but the power input is prohibitive. And acoustic fusion was quite a sordid soap opera back a couple decades ago. People weren't really able to replicate that. But even if you could, the thermal conduction losses through the fluid would just eat you alive. And then there's the idea of very simple beam target experiments. This was very popular back in the 1950s, 1960s. The problem with this is also the thermal conductivity through the target just eats you alive. So this was debunked in one of the first fusion textbooks back in 1960. And if you wait long enough, though, things become popular. So this has become popular again nowadays. No new solutions to it, but very popular nowadays. So wait long enough. I'm still waiting for Space 1999 to become popular again. Other approaches for confinement, you could have a fusion-fission grid that does lead to a lot of radioactivity, a lot of disadvantages when you do it with magnetic or ICF. Ball lightning, I think, is interesting. Nature seems to have some kind of way to confine plasmas, at least at low energies. I've never seen a good explanation for how that happens, especially in view of the virial theorem. And I think people should perhaps investigate this more in the future, see if this could be applied. And somebody at Livermore has even proposed using small black holes to compress and confine fusion plasmas. But of course, the greatest challenge in making dragon soup is always finding the dragon. So are there any other confinement approaches out there, or can we show that all these ideas cover the phase space completely. You folks might want to think about that. Then there's conversion to electrical energy. And are there any better ways, subject to the Carnot limit? You could convert heat or convert the light nuclei. As Livermore found many decades ago, you run into problems with arcing and particles escaping, but maybe there are potential solutions, inverse ion accelerators. Are there better ways to convert energy from the heavy or the recoil nuclei, from the betas, from neutrons, and from the photons? What's the best you can do on energy conversion there? So here is the bottom line for fusion, in my opinion, anyway. Fusion approaches that are not suitable for power-producing reactors include non-magnetic confinement, excluding stars and bombs, which obviously work, plasma systems that try to operate way out of thermodynamic equilibrium, those that use advanced aneutronic fuels, and those, in most cases, that use high-efficiency direct electric converters due to the arcing problems, although there might be some solutions there. So the best foreseeable reactors would use magnetic fusion, as far as I can tell, and would use DT, DD, or D-helium-3. But if you look at a 1 gigawatt electric, 3 gigawatt thermal reactor for those fuels, you find an awful lot of radioactivity. So the selling point on fusion was it's supposed to be relatively non-radioactive. These things are inherently quite radioactive. But there is possible hope. I've gone through and briefly shown you various directions that could be explored more in the future. Are there better fusion reactions out there? Are there ways to use spin-polarized fusion, to use negative particles like muons? Are there ways to improve the tunneling factor? Other improvements to the cross-section? For the fusion products, are there better ways to influence the reaction channels? Are there better ways to manipulate the plasma? Better ways to confine the particles in the energy? Or better ways to convert the electrical energy? So how much would you pay now? But wait, there's more. It slices, it dices. We'll move on. We'll talk about fission. We'll get them annoyed too. So in fission, the idea is that in a very large nucleus, the protons hate each other so much that they want to have a civil war that can release on the order of about 200 MeV per nucleus, or nearly 1 MeV per nucleon. So if you want to do that for energy production, you need a natural source of nuclei like that. There are 3 natural actinides, uranium-235. If we only used uranium-235 to power the whole planet at current rates, we'd burn through it known reserves in about 15 years or so. Of course, there's a lot more U-238, so if you transmute that to plutonium, now you could spend several thousand years burning that. That's just known reserves. There's a lot more out there we could probably find. So this could power the planet for millennia. And thorium, if you transmute that to uranium-233, there's enough of that to power the planet for at least several centuries. If you want to do energy storage, then you are limited not just to natural things, but you can make stuff, even if it requires a large energy investment to make it. So americium, curium, californium, you could make if you're willing to put enough effort into it. And these things are so fissionable, you could put in quite a small fission reactor using these. Of course, the main problem with fission is the waste production. That's kind of inherent in the process, unless somebody can find a way around it. You get a smear of fission fragments produced by this. They're kind of guided, herded into 2 humps by the magic numbers. Because the heavy nuclei have to have an excess of neutrons, when they fission, now they have way too many neutrons to be happy. So they're kind of born natural beta emitters. There's not too much way around that. You also get neutron activation within the fuel that can lead to transuranic production of various isotopes elements. And you can have neutron activation in the other materials in the reactor as well. So bottom line for fission, we know that it works, but are there any ways to make it better? And maybe somebody there would want to think about this. Are there ways to intervene at the nuclear level to make the fission process cleaner, easier, better? Are there better sources, better methods for obtaining fission fuel? What are the best materials to use? What are the best reactor designs to use? What are the most efficient methods for converting fission energy to electrical energy? Is there a way to actually use the kinetic energy from the fission fragments, for example? What are the best ways to use this for rocket propulsion? What are the best ways to separate out the waste or reuse it or burn it up or store it? Probably much better than what we're doing at the moment. And finally, what are the best ways to make fission reactors as resistant as possible to accidents, terrorism, nuclear weapons proliferation, and Homer Simpson? Then there's alpha decay, and this is mainly for energy storage, like on spacecraft going out to Pluto. Although if you consider the source of alpha emitters in the Earth, you get into like geothermal energy with this. So there's a number of potential alpha emitters. Of course, this is used for radioisotope thermoelectric generators, but are there ways to improve that process? Are there ways, for example, you could artificially suppress alpha emission as your probe is in transit out to Pluto? And then are there ways you could artificially enhance alpha emission once your probe gets to Pluto and suddenly needs more energy? Or are there ways you could get improved conversion of that alpha energy to electricity compared to what we have at the moment? I think this is well worth thinking about. Same thing applies to beta emitters, beta decays. Are there ways to improve that over what we have at the moment, to suppress it or to enhance it, or to get higher efficiency? Or with gammas, again, are there ways to improve that, to enhance it, to get higher efficiency? That'd be useful not only potentially for energy sources for spacecraft and things, but I know there's been a lot of interest in gamma ray lasers or the holy hand grenade of Antioch, or creating the Incredible Hulk. Other things, there's nucleon transfer. If you transfer nucleons between nuclei, and if these are nuclei that are in contact with each other, if they temporarily form a compound nucleus, that's just fusion, which we've already covered. If they do not form a compound nucleus, that's a direct reaction, which only occurs at energies too high to be practical for power generation. What about if the nuclei are not in contact? Now, obviously, this happens with fission, with neutrons going from one nucleus to another, but are there ways other than fission to make this happen, to make neutron transfer useful? This has been proposed, it's been investigated. Even Edward Tao proposed a hypothetical particle that might catalyze this. He called it a Meshuggah or a Meshuggah-tron. People have talked about polyneutrons, coherent neutron quantum states, lattice vibrations. Nothing has worked so far, but I think it's worth investigating more in the future. Just to be complete, there's gravitational collapse. So just from a classical back-of-the-envelope calculation, you can show that if you drop things into a very low orbit around a black hole, you can extract some of their rest mass as energy. So from this simple classical calculation, if your black hole is not of the rotating type, you could convert about 8% of the rest energy to useful energy. More detailed calculations than this show it's actually more like 6%. If your black hole is rotating as much as legally allowed, you could convert up to 50% of the mass to energy from this calculation, or realistically more like 42 for more detailed calculations. But compare that, fusion only converts less than 0.7% of the rest mass to energy. So this is converting a very large amount. You could also extract energy from the black hole itself. If the black hole is not rotating, you just kind of wait for a long, long time for Hawking radiation. If it is rotating, though, there are all kinds of things you can do to extract energy via matter, via photons, or electromagnetic interactions. The problem, of course, is there's never a black hole around when you need one. So could you actually create a black hole? And just from back of the envelope calculation, if you calculate the energy required to implode matter to black hole conditions, you end up with numbers, even just to implode 1 milligram to a black hole, you end up with 10 to the 30 something joules. You guys think you've had it hard just getting up to megajoule. Imagine having to get up to 10 to the 35 joules of energy in your project. You can focus energy instead of focusing matter. It works equally well. Requires comparable amounts of energy, though. Still need 10 to the 30 something joules of energy to do that. Or you could potentially collide particles, collide nuclei, heavy nuclei, to create a black hole. The smallest black hole you could create would probably be in the order of the Planck length. If you plug that in, you do the numbers, you need a particle accelerator with about 10 to the 27 or 10 to the 28 EV to do this. And for reference, the largest one we have, the Large Hadron Collider, is only about 10 to the 13 EV. So unfortunately, it's awfully darn difficult to create a black hole. I know everybody's very disappointed by that. And then finally, there's antimatter. And antimatter can annihilate with matter, and 100% of the rest mass goes into energy. This is most useful for rocket propulsion, which needs the highest possible stored energy density. It also limits casualties. If this fails, in the worst case, all you blow up is the Enterprise, and as the movie's already proven, you can always build a new Enterprise. If you do store antimatter, you want to store it in a neutral or semi-neutral state. Otherwise, you run into the Brion limit. And the problem is producing the antimatter, since there's no natural source of antiprotons that we've found. Producing it, you could use a beam-beam collider. This is higher efficiency compared to the other options, but very low production rates, 10 to the minus 5 grams per year or so of antiprotons. Or if you have a beam target collider, you can get much higher production rates, potentially hundreds of grams of antiprotons per year, but lower efficiency. And there are problems with other methods as well. And this is written up in one of my papers, if anybody's curious. So I will stop there. Hopefully I've shown you various directions that people might think about more in the future, or maybe some Tony Stark out there can find some way I haven't even discussed to better extract this energy. So I'll stop. Are there any questions, suggestions, torches, pitchforks?
Thank you. Let's thank our speaker for the great talk. And if you have any questions, you can put them in the chat field or send a note to me and I'll call on you. And I guess there are already a couple comments in the chat. So Morty Rosen commented that the quarter-ton TNT of energy is true, but it's a firecracker worth a momentum impulse. And there's a comment from Ali Ami, said, no pitchforks, I'm loving this as a healthy dose of much needed medicine and pragmatism.
Well, thank you, I appreciate it.
So from Daniel Thorne, you're advocating for magnetic fusion, mainly the tokamak type?
I'm not really advocating for anything. I'm looking at things that don't seem to work as far as I can tell. I'd love to be proven wrong. I mean, I'd love fusion work, but I can divide it into things that don't work as far as I can tell, and then things that might potentially work. At least I can't rule them out. So in the category of things that might work would be magnetic fusion with DT, dihelium-3, or D. I can rule out essentially all other magnetic fusion. It may be that even those are impractically difficult, but at least I can't rule them out. But in terms of what I'm advocating, if anything, I'm advocating for people to go find something better, because even those things are not good enough, in my opinion. So, look at this chart, look at the other things, see if you can find some better direction that people have overlooked, maybe even I've overlooked.
Thanks. And there's a question from Maxim Omansky, who says, what is your view of fusion-fission hybrids? The fusion part does not have to be more than a neutron source.
Yeah, it's a great question. People have certainly looked at that, and the two reactions play nicely together, which is why it's so tempting. In the studies that's been done on that, and people in the unclassified literature mainly looked at it for magnetic hybrids, but I'm sure you guys have probably considered it for ICF as well. But it tends to get quite radioactive, and yet you still need the fusion part. So creating fusion requires lots of very expensive, very high-tech toys, as you folks know very well. And so a hybrid has kind of the disadvantages of fusion, all this really expensive, really high-tech stuff, and the disadvantages of fission, all this radioactivity. So it's kind of the worst of both worlds, at least so far. But maybe there's some better way to do it. Maybe you can find something.
And Jeff Colvin said that there's a lot here to chew on. Can we get a copy of your slides? And since you've already given me permission to pass them out, just email me. I put my email address in the chat field, and I will forward them off to you. From Omar Hurricane, the analysis of solar fusion and solar panels, clear winner at this point or not?
Well, it works very well in the sun. In terms of on Earth, you have to worry about conversion efficiencies and cost for the solar panels and how long the solar panels will last. I've not looked at that in detail. But essentially what I've done here is to look at all methods I could think of for converting nuclear energy in a lab. But then there are all methods you might think of for renewable energy. You could do a whole large survey of that, and all methods for potentially improving fossil fuels. You could do a large survey for that. So this is really just a subset of the whole energy field.
Thanks. And from Trevor Hutchinson, if BREMS won't work for proton boron fusion, do you know why tri-alpha energy is attempting it with field reverse configurations? Surely they're aware of radiative losses.
They've not released that much information publicly on what they're doing. So, maybe they have some Tony Stark who's found some much better revolutionary way to make it work to catalyze fusion or something. But if they've not, if they're just kind of doing what all the rest of us are trying to do, then as far as I can tell from the equations, they don't have a prayer of making it working. So in my PhD thesis, I can show that, unless a miracle occurs, unless you have catalyzed fusion or something, that even under the optimal conditions, best possible conditions, best possible reactor, very generalized to any type of reactor, FRCs, anything else, that the Strahlung exceeds the fusion power. And even if you can argue your way down, Bremsstrahlung equals the fusion power. Again, that's the best possible case. It's going to be worse under practical conditions. And Bremsstrahlung is just one of many loss mechanisms. I was being optimistic and ignoring all the losses from the ions and the losses from the electrons and the losses from synchrotron radiation, all the other losses out there. So, unless they've discovered something wonderful in their basement, as far as I can tell, they don't have a prayer of making PB11 work.
So Brent Blue asks, hasn't tri-alpha energy moved away from energy and moved to isotope production?
I have heard some things along those lines. I'm not a tri-alpha expert, so I don't really know.
Okay. And from Dave Strozzi, any thoughts on magneto-inertial schemes like shear flow, stabilized Z-pinches, dense plasma focus, etc.?
It's a great question. I'd be happy to look at that more in detail in the future. So if you know the best papers, the best approaches, well, please send those to me. From what I've seen so far, they generally would suffer from the problems that magnetic fusion has, or the problems that inertial fusion has, or some combination of those two. But I'd be happy to look at it in more detail in the future.
I'm not sure what Michael Anderson's comment was with respect to. He just says the synchrotron bomb ... But
Sounds fun.
okay. Are there any other questions? Well, if not, thank you for the wonderful talk. I think people enjoyed it, and I hope everybody has a great rest of your day.
Thank you very much. Thank you for
Very much.
hosting. And if anybody's interested, it's all available on my website. So you can find these slides and the papers I mentioned all on my website, so writerinstitute.org. Thank you.
Yeah, thank you. And if anybody'd like to meet with Todd, you can send me an email and I can connect you too. And hope to see everybody back next time. Bye-bye.